Transformations of exponential functions. In this video, we're going to explore the characteristics that can change the shape and size of an exponential function. You will explore exponential transformations and translations vertically and horizontally. We will develop this equation y equal ab to the exponent k times x minus d plus c as we work through this video. Here are the transformations and translations broken down for you. So f of x is equal to a times f of x. F of x can be f of x plus c. F of x can be f at x minus d, and f at x can be f at kx. What type of transformation does each of these represent as they relate to exponential functions? Let's take a look. Sample number 1. Sketch graphs of the following functions using the parent graph y equal 3 to the exponent x as the base. Describe the effects, if any, on the asymptote, the domain, and the range. So we'll have equation A, which is y is equal to 3 to the exponent x minus 4. Equation B, y equals 3 to the exponent x minus 2. And C, y is equal to 3 to the exponent x plus 1 plus 3. If we take a look at sample number 1, the first thing we did is we graphed the parent y equals 3x. We have that represented on our graph with the purple graph and the dotted red line that represents the asymptote. And if we look at the function y equals 3x, we will see that it passes through the point 0, 1, and it then passes through the next point at 1, 3. These are going to be our two comparison points. Now we're going to look at what happens when we add the negative 4. So we will see that our original point of 0, 1 has moved down and become 0, 4, which is the point on the y-axis that the green graph passes through. We will see that the horizontal asymptote, which is represented by the blue dotted line, is now at y equal to negative 4, so it has been shifted down as well. And the point we had at 1, 3 has also shifted down to become 1, negative 1. So what we see that the negative 4 represents is a shift up or down by the number of units represented. So we can say then that we have a translation of the horizontal asymptote down 4 units, but the domain remains the same. We have x as an element of the real numbers, but the range changes, still an element of the real numbers, but now it is greater than negative 4. Now here is sample number 2. Y is equal to 3 to the exponent x minus 2. Again, we have the purple graph representing the original, y equals 3x, and the green represents the shift or the change. And what's happened here is that the value of x has moved 2 units to the right. So it's a shift to the right. And we can see that if we compare the original point of 1, 3 with the new point of 3, 3. You can also look at the point 0, 1, which was the y-intercept of the original graph, and it has now shifted over 2 units as well to become 2, 1. The horizontal and vertical translation, sample number 2, we can see that the translation has shifted 2 units to the right. The horizontal asymptote remains the same, y is equal to 0. The domain remains the same, x is an element of the real numbers. And the range remains the same, y is an element of the real numbers, and y is greater than 0. Now, let's take a look at one that combines both. We have y is equal to 3 to the exponent, 3x plus 1 plus 3. So this will have both a vertical and a horizontal shift. The translation will be left 1 unit, which we can see if we compare the points, and it's gone up 3 units. So the point 0, 1, we can see has shifted and moved up. Now let's look at stretches, compressions, and reflections. Sample number 2. Graph each function to illustrate the transformations being applied. A, y is equal 4 to the exponent 2x. B, y is equal to negative 2 times 4 to the exponent x. And C, y is equal to 4 to the exponent negative 1/2 x. If we look at y is equal to 4 to the exponent 2x, with the purple being the original function, 4x, and the new one is green, 4 to the exponent 2x, and we take a sample point, 1, 4, on the original, we will notice that it is changed in the new one to become 1/2 and 4. We will notice that the point where it crosses the y-axis is the same, and the horizontal asymptote is the same. So what has happened here is that the graph has changed its shape, and we call this a compression by a factor of 1/2. So the 2 in front of the x, in fact, makes a compression of 1/2. So the point 1 becomes 1/2. Stretches, compressions, and reflections, sample number 2. In this example, we're using y is equal to -2 times 4 to the exponent x. Start by graphing y equals 4 to the x. We will use 2 points. X is equal to 0, so y will be 1. So we have the point 0, 1, showing you that on the graph. And then x will be 1, so y is 4 to the 1, which is 4, which is the second point that I'm giving you on the graph. The graph we're using is the magenta, purplish color, pinky purple color. Okay? Now, we'll then apply the 2 in front. So let's calculate our 2 points now to show you what has happened. So when we substitute in 0, we will now get the value 2. And when we substitute the point 1 for x, we get 8. So now we have the 0, 1 moving up to 0, 2. I've shown you now with the up-down arrow. And the 1, 4 to 1, 8 shows you again that it has moved up. So we can say at this moment the graph is vertically stretched by a factor of 2. But now we need to look at the negative sign in front. Continuing on with our example, now what we're going to do is we're going to add the negative in front of the 2. So now we're going to show what y equals -2 to the 4 to the exponent x does. So our points we were tracking are 0, 1. And what happens now is the -2 is the new result for y after our stretch and our reflection. So it's coming down to -2 on our aqua color graph. And the point that was 1, 4 now stretches and reflects to be 1, -8. So it's gone from the green graph 1, 8 down to the 1, -8 on the aqua color. In this sample, y equals 4 to the exponent -1/2 to the x. We're going to graph the original graph, 4 to the x, which is our magenta color. And then we're going to graph y equals 4 to the 1/2 x, which now is our green color. And you will see how our graph has moved over, and in fact, it has doubled. So the 1/2 in front has in fact doubled, stretched by a factor of 2, which is the inverse of 1/2. So you will see the 4 to the exponent 1/2 x is a horizontal stretch by a factor of 2, which is the inverse of 1/2. Now, if we then take the next step and we add the negative 1/2, you are going to see the aqua graph, which is our final graph, which is a reflection around the y-axis. So it's like it's inverted around the y-axis from 4 to the exponent 1/2 x. So the negative as part of the exponent is a reflection around the y-axis, and that's the result that we have. So we add the effect of the negative exponent, we compare the green graph and the aqua graph, and it can be seen that the aqua graph is a reflection around the y-axis. So if we take the summary of y is equal to a b to the exponent k, x minus d plus c, and we graph an example to illustrate this of negative 2 to the exponent 2, x minus 3 plus 5, we drew the original, which is the dark blue color, and now we have our reflection for number 2, which is in the aqua color. It's compressed horizontally by a factor of 1/2. It's shifted right 2 units, which is a horizontal translation. It's shifted up 5 units, which is a vertical translation. So to summarize, A is a vertical stretch or compression. K is a horizontal stretch or compression by the inverse factor. D is a horizontal shift, right or left, which is a horizontal translation. C is a vertical shift, up or down, which is a vertical translation. And negative is a reflection either around the x-axis, if it's with A, and around the y-axis, if it's with K.